Second example, a tightly structured string with fixed endpoints x equal to 0, x equal to L. So length of the string is L, is initially at rest in its equilibrium position. If it is set vibrating, giving each point a velocity 3x into L minus x, find the displacement. So length of the string is given as L. So one end is x equal to 0, another end is x is equal to L. And it is given it is initially at rest in its equilibrium position. So now step 1, we have to write the governing equation, that is one dimensional wave equation, that is equation number 1, similar to the first example. Then we have to write the boundary and initial conditions. So first two conditions are based on boundary. Always there won't be any displacement in the boundary. So same condition, y of 0 comma t equal to 0 for all t greater than or equal to 0, y of L comma t equal to 0 for all t greater than or equal to 0. If I am giving the string length is 2L, means you are supposed to write here 2L at the end x equal to 2L, y is 0. So the next initial condition means at time t equal to 0, what is the displacement? It is given in the problem clearly. It is at rest in its equilibrium position. I already gave a note. If it is given, if it is rest in equilibrium position, you should consider the displacement is 0 at time t equal to 0. So you have to take y of x comma 0 is equal to 0 for x lies between 0 to L. And the fourth condition is velocity. Velocity at time t equal to 0, in the problem itself it is given velocity is 3x into L minus x. So dou y by dou t at time t equal to 0 is equal to 3x into L minus x for x varies from 0 to L. So these are the four boundary conditions you have to list here. Then next we have to write the proper solution for one dimensional wave equation. So that you should take it as equation number 2. This is similar to the previous problem. Applying boundary condition 1, will get A is equal to 0. Applying boundary condition 2, will get lambda value, which is n pi by L. This is similar to the previous example. Then after finding A and lambda, substitute and rewrite, update the solution and take it as equation number 3. Then in this problem, the third condition is 0 condition. So we can use the third boundary condition. And then we should write the most general solution, and then only we should use the non-zero boundary condition. So now I am going to apply this third boundary condition, that is displacement is 0 when time t equal to 0 in equation number 3. Substituting the condition on equation number 3, y is 0, displacement is 0 and time t is 0, means sin 0 is 0, cos 0 is 1. So C alone will be here equating to C to 0, because B cannot be 0 as A is 0 already. So we get C as 0. So substituting C as 0 in equation number 3, we can update the solution as B sin n x by L. C will not be there, C term will not be there. Then D into sin n pi at by L. Then combining B and D, we can write it as Bn, and we can write the most general solution as summation n varies from 1 to infinity Bn sin n pi x by L sin n pi at by L. Previous problem we had cos here, because in previous problem we got D0, because velocity is taken as a boundary condition. Here displacement is 0, velocity exists. So displacement is 0, third condition is 0, displacement is 0 at time t equal to 0, means we will get the value of C as 0 in this. So we got this most general solution. And after most general solution, I have to apply the fourth boundary condition on this. To apply the fourth boundary condition, I need the partial derivative of y with respect to t. So partially differentiate this expression with respect to t, treating other terms constant. So if I differentiate all these terms or constant term, retain it as it is. Differentiate sin, you will get cos n pi at by L, and if you differentiate this n pi at by L with respect to t, you will get n pi a by L. Now apply the boundary condition, that is dou y by dou t at time t equal to 0 is 3x into L minus x. So velocity is 3x into L minus x at time t equal to 0. So right hand side, if I substitute time t as 0, cos 0 is 1, I will get this expression. Now in this expression, this n pi a by L is constant, this Bn is also constant. So combining these two constants together, I can write it as one single constant, which is small bn. So I am rewriting the equation as small bn sin n pi x by L, where small bn is capital Bn n pi a by L. Next, if you see this expression looks like Fourier of range sine series of the left hand side function, which is a function of x. So therefore the formula for finding the small bn is 2 by L integration 0 to L. This is the function which is there in the left hand side, f of x sin n pi x by L dx. This is the formula from Fourier series, off range Fourier series. This L is the length of the string. So according what is the length of the string is given, L is given, we should substitute that value here. In this problem is concerned, the length of the string is L, so we are writing the formula as it is 2 by L 0 to L, the function which is there in the left hand side, into sin n pi x by L dx. Now we have to integrate this using integration by parts. So 3 into 2 is 6, take that 3 outside, 6 by L is constant, take it outside. So remaining this term you should take it as u, remaining term is dv. So first write that u term as it is, integrate this dv and write it here, it is v. I am using integration by parts, general formula. So first term and all u's you are supposed to differentiate, v's and all you should integrate. So first term if I differentiate, I will get L minus 2x, alternatively positive and negative sign should come. Then if I differentiate this sign, I will get cos, this cos if I differentiate I will get minus sign. So sorry, is this cos I am integrating, so it is plus sign, already a minus sign is there, I am writing that minus sign here. Then next plus, if I differentiate this minus 2x I will get minus 2, if I integrate sign I will get minus cos, so minus of minus plus cos n pi x by L divided by, the coefficient of x is n pi by L, so that n pi by L I have to divide, so altogether n pi by L the whole cube. Now the next term will not exist because derivative of minus 2 is 0. So expansion stops here and the limits are from 0 to L. So first substitute the upper limit for x as L, you will get this, and lower limit as 0, you will get this. So subtracting these two, you will get this expression. Simplifying further, I will get small bn as this, but we need what is capital Bn to be substituted in equation number 4, which is the most general solution. So therefore equate this to capital Bn n pi a by L. So bring this n pi a by L to the other side and simplify, you will get it as 24 L cube divided by n power 4 pi power 4 a, if n is odd, if 0 if n is even. What is this if n is odd and even means? It is from this step. We got cos n pi here, the value of cos n pi is minus 1 the whole power n. Okay, so this if you substitute n as 1, minus 1 the whole power 1 is minus 1 minus of minus, it is plus, you will get the value as 2. If I substitute n as 2, minus 1 the whole square is plus 1, so 1 minus 1 will become 0. If I substitute 3, I will get minus 1. If I substitute n as 4, I will get plus 1. So whenever I am taking n value as odd, this term will exist and I got the value as 2. And whenever I am taking n as even, I am getting this term as 1. 1 minus 1 will become 0. So therefore I can rewrite the solution exists only for odd values of n. So it is 2, this gives the value 2 if n is odd. So 12 into 2 is 24 L squared by n cube pi cube if n is odd, 0 if n is even. So this n pi a by L I should bring it to the other side, and that is the value of Bn, which I have to substitute in equation number 4. So equation number 4 is the most general solution. And while writing the summation here, you should write n exists only for odd numbers, right? So it is 1, 3, 5 etc. up to infinity. Then this Bn value I should write. Then that sign term n pi x by L and another sign term n pi at by L. Now the summation should not be discontinuous like this. So we have to rewrite this as continuous number from 1 to infinity. So what we should do here is, if this odd number, remember to replace n, wherever n is there, remember to replace n as 2n minus 1. If you do so, 2n minus 1, you can rewrite the summation continuous from 1 to infinity. So if I substitute n as 1 in this, wherever n is there, I should write n as 2n minus 1. So now if I substitute n as 1 here, I will get 2 minus 1, 1. So 1 I am getting. If I substitute n as 2 here, 2 into 2, 4, 4 minus 1, which is 3, 3, the next odd number. So I will be getting only odd numbers here if I substitute all the values of n from 1 to infinity. So if it is odd number, you remember to replace n as 2n minus 1 here and also here. and if you are getting these numbers are even numbers, you should replace n as 2n. Next example we'll see in the next lecture.